So today we're going to be looking at Algebra 2, Big Ideas, section 6.1, which is graphs of exponential parent functions. In the previous chapters, we've studied other parent functions, linear, quadratic, cubic, square root, etc. And now we're going to be looking at a group of functions that are called exponential parent functions. The reason why they're called exponential parent functions is that the variable is in the exponent. So in the examples that I have here, those are, you can see that the x, which is the independent variable, is in the exponent of the equation, and that's what makes them an exponential function. So if you have a graphing calculator, or you can use an online platform as well, to get an idea, just basic idea of these graphs, pause the video perhaps and graph those, compare them with each other and see if you can make any observations. And then we're going to talk about them in just a sec. So if you've done that, if you've paused the video and done that, that's great. If you haven't, then we're going to talk about them anyways. If you look at y equals 2 to the x, here are some things that you may have noticed about it. It goes through the point 0, 1. It has this general shape here. It looks like it goes through the point 1, 2. I can also see that or verify that from looking at the table in the calculator that it would go through the point 1, 2. And it would go through the point 2, 4. But as far as grid marks, that's what I'm looking at. I'm not really sure by looking at the graph what points it would go through over here. Now if I go to the table, I can actually see that it goes through the point -1, 1/2, and then -2, 1/4. And so I can comment about the domain and the range of this. The domain is all real numbers. The range is that y has to be greater than 0, or 0 open bracket to infinity. This is an increasing function throughout. It is monotonic, means it's going the same direction the whole time, that it never decreases. It goes up as you read this function from left to right. So we can talk about all those different characteristics of the function. Now let's compare it with y equals 5 to the x. So if I graph y equals 5 to the x on the same axes, I see that y equals 5 to the x also goes through the point 0, 1. But it's above the original function to the right of the y-axis. In fact, it's pretty steep here. Make sure it passes the vertical line test, but it's pretty steep there. And it goes through the point 1, 5. And then on the left side of the y-axis, it's actually underneath the other function. So it may have been an easy assumption to say that 5 to the x is a stretch of the function 2 to the x vertically, but that is not the case because they both go through the same point 0, 1, and it's not a stretch with the y values. We can't see what points this one would go through other than the points 0, 1, and 1, 5 unless we look at the table. And so we can go ahead and consult the table. In fact, I'm going to look at the table of both functions together here. If I look at x, and then I'll look at the first one, which is 2 to the x, and then the second function I've put up here, which is 5 to the x. For the x values of -2, -1, 0, 1, and 2, the function y equals 2 to the x goes through 1/4, 1/2, 1, 2, and 4. And the function 5 to the x, as you can see from your calculator, would go through the points 1/25, 1/5, 1, 5, and 25. Your calculator is going to give you most likely decimals instead of fractions, and you could convert those to the fractions that I have in this table here. So the first difference with exponential functions from the functions that we've studied earlier is that each base counts as a different parent function. So the 2 here is called the base, and the 5 here is called the base of the exponential function. And those are not A, B, C, D transformations. Those are actually just, they create a different parent. So for the parent function that we want, we're going to use a base of k, the number k, so that we can have this table made for any base that we may come across. So again, if you'd like to potentially pause the video and then see if you can figure out, based on the first 2 functions that we did, what points would actually, what y values would be in the k to the x column there. The 1/2 to the x, which is the third one that I have over here, I have an example for you. We're going to come back to that in a little bit. So if you have looked at y equals k to the x, hopefully, you've come across these parent points that you'd have 0, 1. One of the patterns that I notice about these other columns is that as one y value goes to the next y value, in this first column here, I'm multiplying the y value by 2 every time. So to get from 1/2 to 1, or 1 to 2, or 2 to 4. And then in the 5 to the x column, to get from 1/25 to 1/5, I'm multiplying by 5. To get from 1/5 to 1, I'm multiplying by 5, etc. The x's, I'm simply adding 1 every time in the x's. So the x's are being added, but the y's, the pattern created is multiplication. Going along with that pattern, and if I know that it's going to have 0, 1 in the parent function, because anything to the 0 power is 1, then I know that the pattern here must be that I'm multiplying by k to move forward in the pattern. So 1 times k would be k, and then k times k would be k squared. And if I'm multiplying by k to go forward, then I must be dividing by k to go backwards. So I get 1 over k and 1 over k squared. And then I can see that if I'm moving forwards here, that I would be multiplying by k each time. These are the parent points for y equals k to the x before we would start transforming it in a few sections. The graph of this function, if it's like the first 2 that we did, would have this approximate shape, and it would go through the 5 points that I have listed on the table. So I'm not going to relabel them on my graph here, but you may if you want. And the domain is all real numbers, and the range is open bracket 0 to infinity. However, if we go back to the page that we were looking at before and we look at the 1/2 to the x, you'll see that that function, if you graph that in your graphing calculator, doesn't have quite the same shape. If we graph 1/2 to the x equals y, we can see that it goes through 0, 1 like the others. However, it goes through the point -1, 2, and -2, 4, and 1, 1/2, and 2, 1/4. In fact, it looks like the exact y-axis reflection of y equals 2 to the x. Well, if I'm multiplying by a base of 1/2 every time I move forward in the x direction, it would make sense that this graph would be decreasing because 1/2 is less than 1. So I would be multiplying by a number less than 1 as I move forward in the graph. So this graph here assumes that k is greater than 1, which would make growth. So if the base, which is k, is greater than 1, then that's going to produce exponential growth. If k is in between 0 and 1, that's going to create exponential decay. if k would equal 1, if I just had y equals 1 to the x, well, 1 to any power is 1. So that's actually not an exponential function. That's a constant function. So k is not ever going to just equal 1. Also, if we had y equals 0 to the x, then 0 to any power is 0, except for 0 to the 0 power, which we'll leave for a rainy day. And so that's not exponential either. And the base is never going to be negative either. And so your base is always going to be either in between 0 and 1 or greater than 1, because these do not produce exponential functions. Another characteristic that is new for you with this function versus the other functions that we've studied this year is that no matter how far I go over here on this function in the negative x direction, I'm going to keep getting smaller and smaller and smaller, but I'm never going to touch the x-axis. I'm going to keep getting closer and closer and closer and never touch it. So I can draw in a line to guide my graph, and I'm going to make it a dotted line so that it's obvious that this is not the graph itself. This is just a guideline for the graph, and that is called an asymptote. So the definition of an asymptote would be any line a function approaches infinitely. So it's going to continue to infinitely approach. In this case, this line is y equals 0. This asymptote is a horizontal asymptote at y equals 0. It's going to continue to approach that infinitely, but it's never going to touch it. That is just a basic overview of an exponential function and how they are created. So one of the tasks that you might be asked to accomplish would be to make a table and then graph the function y equals 4 to the x. We can do that in the same way that we approached the other ones, now that we have an understanding from the calculator, that if I know that this is going to go through 0, 1, since anything to the 0 power is 1, and I know that my base is 4, so I can say, well, k is 4, so if I move forward in the table, I should be multiplying by 4. So I would have 4 and 16. And if I go backwards in the table, that means I should be dividing by 4, so I would have 1/4 and 1/16. That is a perfectly acceptable way to make this table for the parent function. In fact, that's, I think, generally how I would do it. You can also go straight from the x value to the y value by evaluating the function, which is how the textbook approaches it. For instance, with the x value of -1, I would say y equals 4 to the -1 power, which we know that would be 1/4 to the positive first power, which would be 1/4. So you can go straight from the x to the y by substituting into the equation. Then, from there, I would go ahead and graph them. 0, 1, 1, 4, 2, 16, which is going to be off the graph, and then the others, and I can go ahead and draw them. Be careful that you're passing the vertical line test, that you have arrows at both ends of your function, and then for the points that are not on the grid marks, make sure that you either have those points labeled on the graph or that you include a table of values so that whoever's looking at your function can see it. The asymptote is sometimes necessary and sometimes is assumed. So if the asymptote is on the x-axis itself, then generally that can be assumed. Otherwise, if you've shifted the function up or down, then it would probably be a good idea to draw in the asymptote so that we have that guideline and we know that the function is going to infinitely approach that. So that's just a basic overview of the math, and now we can talk about how we can use exponential functions. So exponential models for money and for population and for half-life and chemistry, there are a lot of models that use exponential functions. And the basic equation for that would be y equals a times quantity 1 plus r to the t power. In this equation, t is going to represent time. R is going to represent your rate of change. It could be growth or it could be decay. And A, which we didn't have in the parent equation, that represents vertical stretch, but that's also going to represent your initial value that the function is going to go through the point 0a. And so in this case, we know that if k is greater than 1, it's growth. But k in this model is 1 plus r. So if 1 plus r is greater than 1, that means that r has to be greater than 0. So if your r value is positive, that would represent growth, and an r value that is negative would represent decay. For example, in the function y equals 32 times 1.03 to the t power. The questions that could be asked are, is this growth or decay? And what is the percent growth or decay? Well, if I break this apart into the models template, then this would be 1 plus 0.03 to the t power. And so since I'm actually adding something to the 1, I know that this is going to be growth. In fact, I'm going to look at that number and I'm going to say that that is going to be 3% growth. I know it's growth because I'm adding it to the 1. The 32 it would be the initial amount, which was not asked in the question. And the 1 here represents the 100% of the initial amount that you start with. Because if I don't add or subtract anything, then it's just going to be a constant line at y equals 32 there. If, for another example, if I said y equals 10 times 0.81 to the t power, and I asked you, is that same questions, is that growth or decay, and what would be the percent of growth or the percent of decay? This one's a little bit trickier, but we want to write it in the same form. So we could write this 0.81 as 1 minus 0.19 to the t power. And so since we're subtracting, and I can see that 0.81 is less than 1, so the base is less than 1, or r is negative, I know that this is going to be decay, and it's going to be a 19% decay once I've changed the decimal into a percentage. So I would have 19% decay with an initial value of 10 units. So every year I would lose 19% of what I had there. Those models you might see, generally you'll see these for population, or this is also the model for simple annual interest. The last model that we have to look at today is for periodically compounded interest. So compounding interest means that we're going to take all of the money that is in the interest bucket and actually add it into your account. You have a bank account that gets interest. And in doing so, then now your bank account is going to start getting interest on the interest that you just put into the account. And so it is compounding or adding on top of itself. The equation for this is an exponential equation. So you've got A equals P times quantity 1 plus R over N to the NT power. May look complicated if you haven't seen it before. It is worth memorizing. You'll be using it not only in this course, but in pre-calc and other courses as well. In this equation, P is your principal, which means your initial starting amount. R is, again, your interest rate, the annual interest rate, but it's expressed as a decimal. So if I give it to you as a percent, if the problem gives you a percent, you would have to convert that to a decimal. N is the number of compounding periods per year. So that means how often is that interest dumped in your account every year? If the account is compounded monthly, then N is 12. If it's compounded semi-annually, then N is 2, etc. And then T here is going to be time in years. A is your ending amount of money. So for our last example here, if you invest $550 at 2% interest, compounded quarterly, we should be able to set up an equation for this and then answer each part of this question. First, how much do we have after 12 years? And then how long until your money doubles? For the first part, let's go ahead and set it up. I'd have your end amount equals 550, which is your principal, times 1 plus 2% expressed as a decimal would be 0.02. And if I'm compounding quarterly, then N is 4. So that would be 0.02 over 4 to the N times T power. So 4 is N and T is 12. So that would be to the 48th power if I multiply those. And then from there, I would go ahead and just type that in my calculator. And once I type that into my calculator, I get that I would have approximately $698.77, which is not bad, right? Now, no bank currently is going to give you 2% interest, but it's nice that all you have to do is keep money in the bank, and then you get money just for keeping your money in the bank. For part B, how long until your money doubles? Well, 2 times 550 would be 1,100. So my end amount would need to be $1,100. And so if I set that equal to 550 times 1 plus 0.02 over 4 to the 4 times, but I don't know t. So I'm going to leave that as a variable. I don't know, currently you don't know how to solve this equation algebraically because it involves logarithms, which we haven't learned yet. So you would use your calculator to graph and solve this problem. We would put one side of the equation into y1 in your calculator and the other side of the equation into y2 in your calculator, and then find an intersection point. So we would see the initial and equation, and then we would see y equals 1,100, and finding that intersection point, we would get, let's go ahead and calculate it, that they intersect at the point 34.744 1,100. So that means that how long until your money doubles would be approximately 34.744 years. So I hope this gives you a nice little overview of exponential functions. We're going to be continuing to work with exponential functions in 6.2 and then also a little bit in 6.4. So happy mathing. Enjoy the rest of your Chapter 6 experience.